So I will start. I will start by. Last time was a little bit fast, so I will re-explain again some of the things that I said last time. So first of all, there is a basis of cycles, of 2G cycles, which you can choose symplectic. So AI intersects only BI in the trigonometric direction. Then there is a basis of one forms of holomorphic one forms that are normalized on A cycles. And then the matrix of periods is the B cycles of this normalized basis. This allows to define the Abel map. The Abel map sends a point to C to a power G, to a vector in CG. By just integrating so you choose an arbitrary base point O once for all, you choose it once for all, and you integrate the one form omega I from O to P that gives a complex number. And this defines the Abel map. So the Abel map is well defined initially only in a fundamental domain. But if you work modulo the lattice of integers on tau times integers, then this extends to the whole surface. Then we have also a theta function that goes from CG to C, which is not exactly periodic, but quasi-periodic. So by composing the two, the idea is that we can get functions from curve sigma to C. That's the idea. The idea is that this will give a basis of all possible meromorphic functions. So let me recall. So let me reintroduce the notion of divisors. A divisor is a formal sum of points. So in general, we shall write D equals sum of Pi, but if a point appears several times, we can have I. Is a formal one weighted by integers. I mean positive or negative integers. Okay, that's the definition. We define the degree of D to be just sum of alpha I. And we define the Abel map U of D to be sum of I of U of Pi, alpha I U of Pi. So basically the Abel map extends to divisors by linearity. So divisor of a function of a form f is just, we call it f is sum of zeros on poles of order so it is just the sum of zeros on poles weighted by their orders. So if you have a pole, the order is negative. If you have a zero, the order is positive. So one of the theorems I mentioned last time is that okay. One of the theorems I mentioned last time, which was very important, that I'm going to comment again on it. If f is meromorphic function, so which I wrote M of sigma, which is the set of meromorphic function. This implies that the degree of the divisor of f is 0, and the Abel map of the divisor of f is 0. And f of p can be written c times product from I equals product over I of a function that I will call gpi zeta of p to the alpha I, where the divisor of f is sum of alpha I pi, and the function g q zeta of p is just theta of u of p minus u of q plus zeta, and where theta of zeta equals 0. I mean a non-singular 0, so on zeta non-singular 0. Okay. And there was also the converse. On the converse, if D is such, degree of D equals 0, and U of D equals 0, then there exists f such that the divisor of f is D. And this f is in fact given by this formula. So, to prove that, well, first this theorem was only for G strictly positive, of course, otherwise there is no Abel map. Let me just mention the case of G equals 0. When G equals 0, I showed you that in fact on any Riemann surface there exists some meromorphic functions with poles of given degree and given at a given point. So imagine you have a Riemann surface. Sigma is a Riemann surface of G 0. So it could look like something like that, but it has no non-contractible cycles. We know that there exists a function. Let's call it phi, meromorphic, with one pole. Let's choose the pole to be somewhere, wherever we like, with one double pole. With one double pole, with one, there exists one form and let's call it d phi with one double pole and then its residue is equal to 0. Because if the residue would be non-zero, it means that there would exist another point where there is a pole. And so, in fact, we constructed it last time with the Dirichlet principle. I don't want to argue on it. But so, since the residue is 0, since there is no non-contractible cycle, it means that the integral of phi is, so phi, this implies that the form d phi is exact. So d phi is indeed the, so phi is a meromorphic function. And it has a triple pole. Sorry, what am I saying? Sorry, it has a simple pole. And thus a simple 0. And the map phi that goes from sigma to C, well, since there is a unique simple pole, you can send it to the infinity in the compactification of C, so into CP1, in the Riemann sphere. And this map, so it means that you have a map from your Riemann surface to CP1, and it's not very difficult to show that this map is invertible. To see that it's well, first you can see that it's injective because if it would be non-injective, there would be 2 points with the same image. Up to a shift of phi, this image could be 0, so it means there would be 2 zeros, but in fact there can be only 1 0 since there is only 1 pole. Okay. So it's an isomorphism. Well, so the theorem is that every genus 0 compact Riemann surface is isomorphic to CP1. So it means we can work with CP1. So now on CP1, so on CP1, every meromorphic function f can be written f of, well, let me call the variable z in the complex plane, so CP1, let me call the variable z instead of p. P was a point on the Riemann surface. Let me call it z when it's on the Riemann sphere. F of z is product of z minus pi to the alpha I. Well, basically every rational function is a ratio so it contains positive powers of some z minus the zeros divided by positive powers of z minus the poles. And we must have, and we always have, sum of alpha I equals 0. There is no Abel map, so there is no such condition. And vice versa, if you choose any points on sum of alpha I is equals 0, this is a meromorphic function.
Do you allow infinitely many zero-one poles, or
No, finitely.
finitely?
You are on a compact surface, so if you would have an infinite number, there would be an accumulation point, or it would not be analytic. So, it's just to say that this theorem, in fact, also holds for genus 0 by replacing the g, so the theta function, by just p minus q, basically. So this is just to say that this theta function is in some sense what replaces the monomials. So so now let's see why it's true for higher genus. So why it's true for higher genus? The subtle point, which I didn't speak much about last time, is that this function, g, so let me rewrite it here, gq zeta of p, which is defined by theta of u of p minus u of q plus zeta. Well, by definition, since zeta is the zero of theta, this vanishes when p equals q, of course. So it vanishes when p equals q, but it vanishes in other points. In fact, it has this function has g zeros in the fundamental domain. Remember that the fundamental domain is just obtained by cutting. By removing all the A and B cycles. So it has G zeros in sigma 0. One of these 0, 1, 0 is Q, of course. And the others are P1, P index G minus 1. Okay. So, which means that when you take ratios, so you know that this quantity product of g pi zeta of p to the alpha I, sorry, these are not the same pi's. Let me call them p tildes. These are not the zeros of poles. So, this function could in principle have these points as poles or zeros. Well, the idea is that these points, p tilde 1 and so on, p tilde g minus 1, they are functions of q and zeta. In principle, they are functions of q and zeta. The trick is to show that, in fact, they are not functions of q. They are only functions of zeta. So now I'm going to use another theorem before proving that one. Theorem. So let theta written like that be the set of all zeros of the theta function. And let W in the P minus 1 be the set of divisor which are sums of G minus 1 points. So typically of the form G equals P tilde 1 plus P tilde G minus 1. okay, no, let's give another name. P hat 1, P hat G minus 1. What we are going to show is that there is a bijection. So the theorem is that there is a bijection between theta to WG minus 1. There is a map from theta to WG minus 1, and which is invertible, which is an isomorphism. And in fact, this is very easy. We already have all the ingredients. We know that for fixed Q, at fixed Q, at given Q, we just associate to zeta, we shall just associate the points, the divisor p theta 1 of Q zeta plus p theta 1, p tilde index G minus 1 of Q zeta. We shall associate that divisor. But it could depend on the choice of Q. The trick is that the inverse map, well, another thing is that theta is defined on C to the power G, which is a G-dimensional space. The set of zeros should be typically a G minus 1 dimensional submanifold, codimension 1 manifold. So it should be of dimension G minus 1. W G minus 1 is of dimension G minus 1 locally. So they have the same dimension. Moreover, it's easy to see that the map is locally invertible if zeta is a non-singular zero, because just locally you can compute the Jacobian. It's made of derivatives of theta. So it's typically non-vanishing. And the inverse map is just, so if you have such a divisor, the inverse map, remember, was k minus u of d. Where k is the Riemann constant, k was the Riemann constant, it belongs to CG. It's a vector, and u of d is just the Abel map of the divisor. But you see that the inverse map is independent of Q. The inverse map is independent of Q's, which means that the map is independent of Q. So this is an important theorem saying that the set of divisors, the set of divisor of theta is isomorphic to the sum of G minus 1 points. So every zero of theta is k minus the Abel map of a sum of G minus 1 points. And vice versa, every sum of G minus 1 points, when you take the Abel map and take k minus this sum, is a zero of theta. So this is quite an important theorem that characterizes the set of zeros of theta. And that we shall use a lot, in particular in the proof of Riemann rho. So this is an important theorem, but the consequence also is that p tilde, the points p tilde 1, p tilde G minus 1, so the divisor, is independent of Q. It is independent of Q. So when you take this product, basically the poles and zeros at those points completely cancel. So this is so this was one of the important theorems. In fact, there is another theorem which is quite important, which is the Jacobi inversion theorem. So theorem of Jacobi which says that now there is a bijection between the Jacobian and what I would call WG, which is the sum, the divisors that are sums of points. So every point in the Jacobian is related to a sum, so can be written as the sum of G points. Let me state it well. So if you have, the map is the following. So basically it will map that to, let's call them P tilde 1 plus P tilde G. And the inverse map is simply U of D minus K. So whenever you have a sum of G points, you take the Abel map of this divisor and subtract K, and this is the point in the Jacobi. It is proved in a way very similar. So the way to prove that is that now define another function, define the function, let me call that G tilde V of P, which is simply theta of U of P minus V or plus V. Probably plus V. Okay. It's easy to see that this map must have G zeros by using the Riemann bilinear identity. So basically, knowing the just the behavior of theta at the boundary of the fundamental domain, that it satisfies some quasi-periodic condition. This allows, by Riemann bilinear identity, to prove that this function must have exactly G zeros. And these are the points P tilde 1, P tilde G. No, maybe not exactly. Sorry. It has, so this map has G zeros. That I will call, let me call them Q tilde 1, Q tilde G. So they are function of V. Okay. So in particular, this implies that if you take U of Q tilde 1 of V plus V, by definition, it's a zero of either zero of theta. So either zero of theta. And by the previous theorem, it means that it can be written K minus U of, let's call them P tilde 1 P tilde 2 plus P tilde G. And you see that it implies that V is of this form. which implies that, so since these two, so this implies that V equals K minus, so probably I should have taken minus V. So minus V, so which implies that K is minus K plus U of Q tilde 1 plus P tilde 2 plus P tilde G. So which implies that indeed we have a divisor made of G points. And vice versa, the inverse map is exactly that. So this just says, so it may look complicated, but well, you have here something that locally is like C to the power G. And we have seen that the Abel map embeds the curve into the Jacobian. The Abel map embeds the curve into the Jacobian, but in a way which is very complicated. It's nonlinear and so on. And somehow this says that there is a kind of inversion. A point in the Jacobian can be somehow re-expressed in terms of points on the curve, but since the curve has complex dimension 1, and CG has complex dimension G, of course, the embedding of the curve is much smaller than CG. So it's not so there is not so a point in the Jacobian is not necessarily in the image, but it is always in the image of a sum of G points, which is non-trivial, which is quite powerful.
I have a question. So the map associating B to P1 plus PG. So these P1 and PG are the same P1.
Yeah, yes. So again, it may look like here I have made a choice. I have chosen this one, Q1. I could have chosen Q2 and so on, but the idea is that because the inverse map is independent of that choice, it means that the map this way was in fact also independent. So in fact it means that Q tilde 2 plus Q tilde G is equal to that, in fact. In fact, the Q tildes and the P tildes are the same. So it implies that afterwards. Okay, I know this is quite abstract, but I wanted to mention it. We are not going to use it, but this is one of the most important theorems in the domain. Now let me go to the Riemann-Roch. One. So this is chapter 4. So the question that we want to ask is, given some points on some degrees, so the question given some points, let's say P1, Pn on sigma, and alpha 1, alpha n integer numbers, is there a function or a one form such that, well, let's call it f, such that F has poles or zeros of order at least those given by the alpha i's. So at pi, so is there such a function? And what is the set of such functions? So we shall put some definitions. We shall define an ordering of divisors. We shall define positive divisors. D is said positive if and only if all alpha I are positive. So D positive. So we also say that D is strictly positive if and only if D is positive and D is different from 0. Okay, and we shall say that now we shall define an ordering. It's a partial ordering of divisors. D is larger than D prime if D minus D prime is positive, of course. And D is strictly larger than D prime if D minus D prime is positive. So this is just to give a definition corresponding to orders at least. So then another definition. I'm going to define the indices. Index is that so let D a divisor, an arbitrary divisor. Then I will define L of D to be the set of functions, of meromorphic functions f such that the divisor of f is larger or equal to D. And I will define the index R of D to be the dimension of that space. Okay. Well, first of all, so it just means the set of functions whose poles and zeros are of order at least those of D. So if there is some alpha I which is positive, it means you want the function to have a zero of that order or higher order. And if there is a pole, you want to have a pole of at most that degree. At most minus alpha I. Alpha I is negative. And so, first of all, this is clearly a vector space. I mean, linear combinations of elements of that space are in the space. So every linear combination is in the same space. So you have a dimension.
Why is it bounded?
Sorry?
Why is it bounded?
Why is it bounded? First of Well, we shall see that in a moment. Indeed.
Complexity, no?
Well, can I find a very simple argument to say that? Yes, I think it's quite easy to find an upper bound, but okay. Let's say it can be infinite for the moment, but in fact we shall see it cannot. Let me call omega of d equals the set of meromorphic one forms omega such that omega is larger than d. And I will define I of d equals dimension of omega of d. And then the Riemann theorem first of all, it's not yet obvious that they are bounded from above, but it's obvious that they are bounded from below. The Riemann theorem says that R of minus d equals degree of d plus 1 minus g plus I of d. So this is really the key theorem. You see that you have minus d on one side and d on the other side. So I will start by showing some special cases of that theorem and give you the intuition of why it is true. Just remark that well, why is this theorem useful? Because somehow you have two things that are unknown, R and I, but very often it is very often what you just want to show is that there exists some meromorphic function or some meromorphic form. So very often the problem is to show that there must exist at least one. So basically you want on at least one which is non-zero, because of course 0 is always good. I mean, the meromorphic function 0, the function which is identically 0 always has, well, by definition is always in the set. So, so what I want to say is that what is interesting is when you have R of d strictly positive or I of d strictly positive. Otherwise, it means you have only 0. So, why is so? The interesting question is are these numbers positive, strictly positive or not? So basically, you want to find the existence of functions with given poles and zeros, or existence of one forms with given poles and zeros. And the fact that you have minus d on one side and plus d on the other side means that very often you have a lower bound. So basically, typically, you will have a lower bound on that side, so which means a lower bound for that one. So you will very often be able to show that it is strictly positive using this theorem. Yes. Another reason why it's useful. Yes. Another thing is that very often one of the two is easy to compute and the other is difficult. So this relation gives you the other. So let me give you typical examples. So first, let's do it in genus 0. No. Yes. First, No. First, let's look at special cases. So this was part 1, and this is now part 2. On part 2, let's consider special cases. And the first special case will be the case where, well, the first special case will just be d equals 0. So basically now L of 0 is the set of meromorphic functions with no poles, without poles. Okay? And basically these are constant functions. We know that this is basically C. These are constant functions, which means that R of 0 is 1. And omega of 0, which is minus d, minus 0 is 0, is the set of meromorphic forms without poles. Which is what I called H1 of sigma. And we know that the dimension, its dimension is the genus. And the degree of the degree of 0 is 0. So you can check very easily that the Riemann-Rohr theorem is satisfied. So Riemann-Rohr theorem is satisfied because 1 equals 0 plus 1 minus g plus t. Okay, that's fine. Let me keep it somewhere. R of minus d equals degree of d plus 1 minus g plus I of d. So which is my thing. So let me consider another special case. Consider another special case, which is the case where minus d is strictly positive. So then L of minus d must be the set of meromorphic function. So remember that this means that minus d is sum of alpha I pi with at least alpha I positive, and at least one of them that must be strictly positive. So it's the set of meromorphic functions with no poles, and at least 1, 0, which is simply, well, clearly there is only, so the only meromorphic function that can satisfy that is the identically vanishing function, which means that R of minus d is 0. Now, now let's consider omega of minus d. Omega of minus d, sorry, omega of d is, so now d is strictly negative. So it's the set of meromorphic one forms. I should have done something first. With poles.
Sorry, didn't you say that strictly positive means that all of the alpha i's are bigger than 0?
No, I'm saying, well, okay. In fact, those that are 0 are not, you can say they are not in the sum.
Silly question. Why do you keep alpha i's if they are 0?
Yes, that's the same question. In fact. So you don't have to keep alpha i's when they are 0. When they are 0. It's just so somehow to be more general. Okay. So a divisor is basically is always such that there is at most a finite number of points whose order is non-zero. So at least on okay. Okay, I agree. You can say just alpha I positive. But in fact, let me not do that now. Let me not do it now, because I forgot to do something before. So let me now consider another case. No, let me now take the Riemann sphere. G equals 0. Let me do that on the Riemann sphere. So we give ourselves a D equals sum of alpha I pi. Okay, and alpha I just belongs to Z. Can we write all meromorphic functions, so rational functions, with poles of order at least minus alpha I, because we take minus D. So what is L of minus D? L of minus D must be the set of all functions of the form C times product of of Z minus pi to the power minus alpha I. So let me write it this way. C times product of Z minus pi to the alpha I times something now that can have no poles. So times a polynomial. Now I think that will answer your question, Renat, to see that the dimension must be finite. Because you want a polynomial so that you cannot introduce higher order poles at the pi's, but you also want that to behave well at infinity. So basically your of degree smaller than sum of alpha I, which is the degree of D. Otherwise, you would introduce a new pole at infinity. Well, let's say none of the pi's is infinity, and if one of the pi's is infinity, in fact, this is true as well. So, what is the dimension of that space? Well, it's easy. It's the space. It's the dimension of the space of polynomials of degree at most d. So it's degree d plus 1. So R of minus d is degree of d plus 1. No, sorry. It's not true because because the degree could be negative. So it's not true. Sorry. R of minus d is the max of 0 and degree of d plus 1. And this max is important. Now, what is omega? What is omega of d? This is the set of one forms. So one forms can be written like constant times dz times and now product of z minus pi to the alpha I times some polynomial q. What is the maximal degree of q? Well, you know that at infinity, dz has a double pole on the Riemann sphere. Remember, because if you use the variable z prime equals 1 over z, which is the good variable in the neighborhood of infinity, you have that dz is minus 1 over z prime square dz prime. So there is a double pole. So dz has a double pole at infinity. So what is the pole of that at infinity? The degree of the pole is basically 2, it's minus 2 plus sum of alpha I. This is the behavior. So basically, when z goes to infinity, I'm missing. Well, minus sum of alpha I. Minus sum of alpha I. Minus sum of alpha I. So you want the degree of p of q to be, so you want the degree of q to be smaller or equal to minus 2 minus degree of t. Okay. All that. So what is I of d? The index I of d is basically the max of 0 and minus 1 minus degree of d. Because the number of polynomial is always 1 plus the degree. So, it's easy to see that in all cases, well, basically you have 3 cases to look at. Degree of d plus 1, is always equal to degree of d plus 1 plus I plus max of 0 minus 1 minus degree of d. This is always true, and basically you have to consider the case where degree of d is positive, negative, equals to 1, minus 1, or 0, and in all cases this is true. Okay. So it means that the Riemann-Roch theorem is always satisfied. So you see that basically, it's what I said before. In the Riemann-Roch theorem on the Riemann sphere, you see it. Basically, most often, one of those two indices is 0, and the other is non-zero. So one is trivial, and the other is more complicated. And so the Riemann-Roch theorem tells you that since there is a relationship between the two, it's obvious to get the other. Well, let's do it Also for the yes, maybe you can take a break. So now, I will consider the next case, which is genus 1. Genus 1. The torus. Notes. So genus 1, so we are on the torus basically. So we know that it can be sent. In fact, in that case, the able map always sends, so the able map always sends sigma to the standard torus, which is the Jacobian. In that case, the Jacobian has the same length as dimension 1. It is exactly the parallelogram. We identify the opposite sides, so this one with this one, and this one with this one. Okay. So this is really the standard torus. But in fact, we shall not use that. What we shall use is that there exists a unique. So there exists a unique one form. So a holomorphic one form, omega, which has no pole and no zero. And unique up to scalar factor. Which means that whenever you have a one form, sorry, let's call it omega 0. Whenever you have a one form, so for every one form omega, you can associate a function which is omega divided by omega 0 for every meromorphic one form. It's a meromorphic function with the same poles on zeros. So basically, the divisor of f is equal to the divisor of omega. It's because you divide it by omega 0, which has no pole nor 0. And the inverse map, of course, is that to f, you associate f times omega 0, which is a one form. So there is a bijection. So basically what I'm just saying is that L of D is isomorphic to omega of D. So which means that R of D equals I of D in genus 1.
Sorry, so to say this, you don't need omega 0 to be unique, right?
No, you don't. Yes, you don't need it to be unique, you need it to have no zeros. That's right. Remember that in higher genus, one form, a holomorphic one form has 2g minus 2 zeros. So it has zeros. It always has zeros, so you can. So one remark is that in the torus, the theta function has only one zero in the torus, and it's exactly the center. Zeta is 1 plus tau divided by 2. It's the unique zero of theta. So now let me define. So now so we shall try to do Riemann theorem f that belongs to L of D. So which means it has given poles on zeros of at least those orders. And first, now remember that for functions, we know that the divisor of f must be, so which means that the divisor of f must be larger than d, but we know, and we also know that the degree of the divisor of f must be 0, and the Abel map of the divisor of f must be 0, because it's a normorphic function. So it means that we shall look for another divisor. And so, yes, f larger than d means that there exists d tilde such that f can be written d plus d tilde.
Excuse me, you will be interested in L of minus d finally.
Sorry?
In the Riemann-Roch theorem, we were finally interested in L of minus d.
Yes, well, we call d minus d. Okay.
Because in the previous examples, so I mean, is it the continuation of the same example?
The general proof.
I'm talking about the general proof for genus 1. Well, since we have that, well, we say, okay, we are interested in L of minus d, but we are also interested in omega of d, which is isomorphic to L of d. So let me compute the index of L of d. Okay. Well, I mean, if you want then to compute the index of L of minus d, you just replace d by minus d in the final formula. So, so I don't want to carry minus signs everywhere, so let me do L of d.
So do you make an assumption on d, or is d arbitrary?
No, d arbitrary. So now d arbitrary.
What is degree of f zero?
Sorry, well, because every homomorphic form must have a degree 0. And must have an Abel map 0. So, so there exists, so by definition of L of D, there must exist a divisor d tilde which is positive, such that the divisor of f is d plus d tilde. So basically the divisor of f, so this is just saying the same thing as divisor of f is larger than d. So this is the same thing. This is exactly the same thing. Okay? And we know that since the degree is negative, it means that the degree of d tilde is minus the degree of d. And we know that the Abel map of d tilde must be minus the Abel map of d. So let me define this space. Let me define the space that I will call V of D, which is the space of all divisor d tilde, such that d tilde is positive, and degree of d tilde equals minus degree of d, and u of d tilde equals minus u of d. And so what I'm saying is that there is an isomorphism between this space and L of D. What I'm saying is that L of D is more or less isomorphic to that space, V of D. That's not exactly true because I will have, so let me write it this way, plus C. What do I mean by that? What is the isomorphism? Well, in fact, let me work the isomorphism in the other way. So to every pair d tilde on a complex number, I will associate the function f of z of p equals c times the product over well, okay. Let me write d equals sum of alpha I pi, and let me write d tilde equals sum of alpha tilde I p tilde I. So you take the product of the theta function of u of p minus u of pi plus 1 plus tau over 2, so which is our 0 to alpha I, times the product over I of theta of u of p minus u of p tilde I to the power alpha tilde I. Sorry, it was minus degree of d. Yes. Yeah, that's right. So it is, you see that this is a meromorphic function on the torus. Each theta is quasi-periodic. So it's not necessarily, so it could be non-periodic on the torus, but the constraint that's, but exactly this constraint on the degree on the use, you can check that the phase, when you go around the cycle, the phase is exactly 0 because of those two constraints. So in fact, it is periodic. So this is a meromorphic function. And vice versa, every meromorphic function can be written in this way. So every meromorphic function can be obtained in this way. And so the question is to compute the dimension of this space. And the dimension of that space is what?
What do you mean by dimension? It's not a linear space.
Yes, it's a linear space because divisors form a linear space.
With this constant?
Yes.
For fixed
linear.
D?
Wait.
Yes.
Sum of I is fixed.
No, sorry. So it's not a linear space. Yes. No, it
What
is
do
a
you mean?
linear space.
You have wait, right.
So, so why should it be obvious?
So how does this isomorphism go?
So,
Mais ça peut pas être un isomorphisme non plus. C'est à cause de la condition de positivité.
Oui.
what do you do?
It's like a half line or a half space, right? Because D is
Yes,
positive. So
You take
a
a
half
D
space
tilde,
is
you
a
multiply
space.
it by -1. Or all
Oh, yeah, yes, sorry. It's this. But so,
it's a quotient, maybe.
Okay.
It's a
But so,
quotient.
there is a bijection between the two. Okay. There is a bijection between the two. Basically, all what you want to count is the dimension as a manifold. So locally. What are the number basically of indeterminates?
Yes.
What are the number of indeterminates and why?
No, it's
do you do that?
between sets. I know, yes.
So
One.
first is if degree of D is positive, sorry, I made a mistake in my notes.
Volume of the polynomial.
I must have made a mistake in my notes, but
But it's basically the volume of a polytop, no? Of an integer polytop. You're counting the alpha tilde, right?
yes, you're probably counting. No, because you don't know where the p tilde is are also.
Ah.
Uh,
So.
Yeah, so oh no, yes, it's because d tilde is positive indeed. So basically you want to find, so yes, first you want to find so if degree of d tilde is negative, then since you want d tilde positive, the only possibility is would be this would imply that d tilde will be 0. So it means d tilde would be 0, and then v of d would be just 0. Would be 0, and which means that L of d should be sorry. Which means that L of d should be sorry. No, what? It depends whether you count
Constant.
So let's take the case where it's strictly negative. Then it's an empty space. V of d is empty. Then V of d is empty. So which means that basically the only thing you have is the constant.
Hmm?
So which means that R of d is 1. Should be 0. Well, no, okay. If you take the formula, you see that there is no
It's an
possibility at all.
empty
it's
product.
0.
Yeah, the product is
Zero.
empty.
You mean this is true if the degree of D is strictly positive, right?
Yes.
Yes.
That's the
But
assumption.
you wrote degree of d tilde as strictly negative.
Yeah, it's a consequence. You will start from the
Yes,
degree of
yes,
D.
so, okay, if you want, if degree of D is strictly positive, then degree of D tilde must be strictly negative, then there is no possibility at all. Okay, so the dimension is 0. Basically, there is only the vanishing function. Now, if degree of D is negative, well, let's consider first the space, the case strictly negative. On the case 0, in fact, the case 0, I did it in the first, I did it, the first case when it was, okay. Let's do case degree equals 0 separately. So, but if the degree is strictly negative, it means that there must, it means that this is non-empty. D of D is non-empty. Basically, it's a set of, V of D is basically the set, locally it looks like a set of, so locally it looks like a set of a certain number of points. It's a divisor made of a certain number of points, and those points are as in the same number as the minus degree of D. So it looks like that. So you have sigma to that power, so it just means that it's a number of such points. But with one constraint. The constraint is that the sum of their Abel map, so on the torus you have a certain number of points, okay? But you want their sum to be 0 modulo the lattice. So basically the number, the dimension R of D is minus degree of D, minus 1 because of the constraint, because you have one constraint, that the Abel map must be 0, and plus 1 because you can multiply by a constant. So it's minus degree of D. So basically, if you, so minus degree of D is a positive number. It's just the number of points that you should choose. Those points can be coinciding. It can be a number of points with multiplicity. And the only constraint that you have to define V of D is that their Abel map must be 0. So we have one constraint. And that's all. So the dimension is quite easy to compute, and it's equal to that. The case degree of D equals 0 is very similar. To do, let me not do it. But so in the end, you can check that what is always true. What is always true is that R of D, which is the same thing as I of D, is the max of 0 and minus degree of D. And you can check that this satisfies Riemann theorem.
When you go to minus D, you get the inf.
Yes, but well, or you can just check the two cases, degree of D positive, degree of D negative, and see that it's always true. Let me do another special case. Now let's take change larger than 2. Now let's take G larger than 2. Let's take the case where degree of D is degree of D. Let's take the case D positive, and degree of D equals 2G minus equals G minus 1. Well, let's do that case. In fact, this case is very close to the general case. What is omega of D? Omega of D is the set of holomorphic one forms. So no poles. No poles because D is positive. And with, so let's write D equals sum of P1 plus P minus 1. Okay, let's write D in this way. Some of the PI's can be coinciding. So it means that you can have, so you could, so basically it's some points with multiplicities. With no poles and with zeros at P1, P minus 1. How many such forms do we have? Well, first we know that for any one form, so any holomorphic one form has 2G minus 2 zeros. And so basically, so which means that degree of omega equals 2G minus 2, and the Abel map U of omega equals 2 times the Riemann constant. In fact, I don't remember if I did it last time, and that's why I'm not sure I did it. Okay. But it's in the notes. So we know that every holomorphic one form has that property. So here, basically, we have chosen only half of the zeros, and we have to find what are the possibilities for the other half of the zeros. Okay. So it means that every omega that belongs to omega of D has a divisor of the form, has zeros at P1, Pg minus 1, and P tilde 1, P tilde G minus 1. So this is the divisor D. So let's call that plus, and this is the divisor that I will call D tilde. So what can be the possibilities for D tilde? Basically, omega of D will be somehow the set of possible D tildes, plus again a multiplicative constant. So what are so the first lemma. So for every D, there exists a unique D tilde such that there exists a unique D tilde with degree of D tilde equals G minus 1, and with Abel map and u of d tilde equals 2k minus u of d. D tilde positive. So how do we do that? This is it's a lemma that I've not used before. So yes. So the idea is that the idea is to prove that k minus u of d. So k minus u of d must be a 0 of theta. Where does this come from? Sorry, I was probably enough. Okay, let me admit this lemma for the moment. But so basically, the idea is that omega is well, basically the idea is that the dimension of omega will be 1. Because well, basically it's unique and it uses the theta divisors, the zeros of theta. I forgot to sorry. Okay, now let's consider the space L of minus d. So we keep the same of functions with poles. So remember that d was positive with poles at p1, p index g minus 1. And again, there exists a unique d tilde positive such that degree of d tilde equals t minus 1 and u of d tilde equals minus u of d. Well, it's more or less the same theorem, the same lemma. And so which implies and this implies that there exists a unique to scalar multiplication f tilde f such that the divisor of f is d minus d tilde. No, sorry, d tilde minus d. me do, well, eventually what I want to prove is that R of minus D equals 1 also. And in the end, the Riemann theorem will be satisfied. Okay. It will be clearer in the notes. Let me do another case.
Sorry, but are you saying that basically in all cases we know not only the relation between these dimensions R and I,
Yeah.
that we also know that
Yes.
there's a formula for each of
Yeah,
them?
yes. In fact, we can construct, we don't know only the dimension of omega of D, we can reconstruct omega of D. We have the basis for omega of D in all cases.
But then why is the theorem formulated as a relation between these dimensions rather than giving these dimensions explicitly?
Well, it was formulated this way, and it has generalization to higher dimensions than Riemann surfaces. It works also for complex manifolds. It works also for some sorts of hyperbonders and all that. And then it can be more difficult to make it explicit. Okay. Let me do another case. Let me do the case G positive, and let me consider the case where D is, or minus D is strictly positive. Okay, I'm sorry, I was a little bit too fast in this case. So, first, since minus D is strictly positive, it's obvious that L on minus D is 0, which means that R of minus D is 0. Now let's again make explicit omega of D. So now it means that D is negative. So, and let's write D equals sum of alpha I P I. We shall make it explicit.
This guy.
So it's the set of forms with and each alpha I is negative. With poles at pi of degree larger than minus alpha. So first, I remind you when we proved the existence of meromorphic forms, we proved that for every p and k larger than 2, there exists a form that I will call omega pk that has a pole at p of order of degree k and no other pole and vanishing residue. Well, it is not unique because you can add to it it was vanishing residue and integral over a cycle of omega pk equals 0. And it is not yet unique, even though I specify vanishing residues and integral over the I of omega pk equals 0. That's what we got from the proof with Dirichlet principle. We got that. And we got something even more precise. So imagine that you have your Riemann surface and P belongs to a chart VP. So where is the vicinity? So you have your Riemann surface, and you take a chart with coordinates in the complex plane with coordinates that I will call phi. The coordinate function will be called phi in this chart. And we know that in this chart, omega pk of Q behaves like 1 over phi of Q minus phi of P to the power k. So d phi of Q plus plus holomorphic. This way. At P times d phi of Q. And then it's unique. There exists a unique one that has exactly that behavior. So, but this depends on the choice of charts and coordinates. But given its choice of charts and coordinates chosen once for all, you have such a unique function, such a unique one for all. Very similarly, we showed that using this Dirichlet principle, we also showed that for every P1, P plus, and P minus, there exists a unique form that we call omega P minus P plus that has a simple pole at P plus with residue equals plus 1, and the simple pole at P minus and residue is minus 1, and vanishing and integral over AI of omega P minus P plus equals 0. There is a unique such form. And so basically now take now omega that will belong to our omega of t. Well, it has poles. So we know that the divisor of omega by definition, so it has poles at pi with degree smaller than minus alpha I. So we can always, so near these poles, we can always do the Taylor expansion near the poles, or the Laurent expansion near the poles, and write that omega of Q must be equals to the sum over I and sum over k equals 2 to minus alpha I of some coefficients that I will can call T I k of those forms omega pi k. So there exist some coefficients. Plus, while we know what the residues are, sum over I of T I, well, in fact, let's call it Ti1. I note there is a shift by 1 of omega P let's say P1 Pi. So if we subtract, so basically this is a combination of meromorphic forms, this is a combination of meromorphic forms, they all have the good poles. So where we define Ti1 is the residue at Pi of omega. Okay, so the difference between that and that, basically if we choose the coefficients to be the good coefficients in the Taylor expansion in the chart, and these to be the residues, then this difference is a meromorphic form that has no pole. So it must be equal to a combination of holomorphic forms. Let me call them Ti omega I. Okay, let me call that Ti0. So which means in the end that every one form omega of Q can be written in this way, uniquely. And every choice of the TIKs and the TI1s and so on TI0s is an element of omega of D. So for every choice of the coefficients T, you have an element of omega of D. And vice versa, every element of omega of D can be written in this way. There is just one constraint, is that the sum of residue must be 0, Ti1 equals 0. The sum of residues must be 0. So what is the number of, so what is the dimension then? It's just the number of independent parameters. So what is the dimension of those numbers? It's the sum of, you see, it's the sum of minus alpha I minus 1 plus the sum over I of 1. So we have one choice of this. Sorry, it's minus alpha I plus 1. No.
No, minus 1. No.
And we have, yes, plus the genus, and minus 1 for the constraint of residues. So I must have made a mistake because we should find the degree, of course. We should find minus the degree, sorry. Sorry, sum of minus alpha I minus 1, there is no minus, of course. Okay, so this should cancel that. And then this is minus degree of D plus D minus 1. So this is our I of D. So as you said, Silva, we have indeed constructed a basis. Not just formed the dimension, we have formed a basis. And it's clear now that it satisfies the Riemann theorem. Because we have R minus D was 0. So it gives you an idea of how you prove the general cases. So the only cases that are really, so you see that when D is strictly positive or D is strictly negative, it's quite easy because one of the two spaces is trivial. The cases that are problematic are the cases in between. And I'm sorry, I was very confused in my presentation. This will be done in the notes. I will stop here. And just to let you know, next time I'm not going to talk about this again, so the Riemann theorem. I'm going to talk about moduli spaces. So what is the space of all possible Riemann surfaces of given genus? given markers or things like that. Well, the idea is that it's a kind of manifold of a certain dimension that we shall compute. It has a certain topology, and also it's not. Well, saying it's a manifold is a little bit. Well, it's not truly a manifold. It's a more complicated object. And its boundary, so it's not compact, it has a boundary. There is a way to make it compact, but when you make it compact, it's definitely not a manifold. It's called a stack. And it basically contains pieces of different dimensions. So that's what we shall study next time.